whenever G x by Fi in US maps on a locally convex topological vector space, which basically means a vector space, a real vector space, a complex vector space, with topology induced from semi-norms. And if K inside this space V is compact and convex, which is preserved by the action, then K has a G phase point. So this is probably not the first definition that one sees when dealing with a meaningful group. Usually the first definition is in terms of mean on the group. So exercise. If discrete, it's the same that there is a functional I, which is defined on bounded functions on the group, real valued, which satisfy, first of all, the mean of the constant function 1 is 1. I is linear. And that if f is positive, then so is its mean. And probably most importantly, f is invariant under the left action of G. So you have hints in your paper, but let me maybe just explain them. If G is amenable, the space of means. So this is what, if I satisfies this, we call it mean. It satisfies also this, it's called an invariant mean. So if G is amenable, the space of means will be compact except when the topology on the dual of the infinity of G is given with the weak star topology. In words, means IN convert them in I if for any function G, you mean IN mean of f, there is the I mean of f. Okay, so I won't say anything more on this side. For the other side, I leave you to fill in the details. For the other side, define, suppose that I have an invariant mean I, define the measure of set A to be the mean of the characteristic function of A, then check that mu is definitely additive. Probability measure G, which is left in vain. Now again, I leave the details to you to check. What one does is that if G now acts on the set K, I pick some point here, and I define, let's call it Y, to be this average of G operating on X, D, G. So you need to explain what do I mean by this, how is this defined, and to show that this is indeed a G invariant point of G in K. Okay? Okay, so that's what it is for. So probably the easiest way to construct a known example of amenable groups are with Foner sets. So G is a discrete finitely generated group. Suppose that I am given F and G, which are finite subsets. So I call them these sets a Foner sequence. If the following is true, whenever I take some element of gamma in G, and I look how much it distorts this set Fn, so look at Fn, symmetric difference gamma Fn. These are the cardinalities. Then as tends to infinity, the effect of gamma gets null. Okay? So maybe some examples. First, no example. So let's take G to be the integers with the additive structure. Take Fn to be minus that. Much better. So I tell you this is a Foner sequence. Why is that? If I take gamma, let's call it now M, in Z, then what I used to put in this line is just Fn plus N, which is minus N and plus N. The size of the symmetric difference. This and this is, well, the only things for a picture. This was minus N, and this is minus N plus N, and plus N. Then the only thing the symmetric difference means in one set and not in the other are these M numbers and these M numbers. So the size of this set is exactly 2M, and when I now divide it by the size of Fn, so I have over 2M, M is fixed, N tends to infinity, so this goes to 0. Okay, so something that one should what more examples will follow is for exercise. Let's start with this direction. If G has a Foner sequence, then it's amenable. So again, I won't show everything, but the idea of the proof is to consider the following means of let fn be the Fuller sequence. And consider the means I am of a set maybe of a function f being exactly the usual average on the set fn. Then one shows that, well, this is a sequence in the space of means, and well, because it is compact, as we already said, it has some converging subsequence, at least ideally. And one shows this condition over there to exactly show that this limiting mean is invariant under the left action of G. Nothing more than that. Okay, so now maybe it's time for more examples. Well, this is a stupid one. If G is a finite group, then Fn is always G is a Fuller sequence. Okay, is this clear? Now what? Still have example we want to do that if G is finitely generated discrete again, and suppose it has sub-exponential growth. So what does this mean? What we explain is this. Okay. Let S inside G finite symmetric generating set. And let me define, and notice the S, and the growth of the group G with respect to S be the number of elements G in G that can be written as a word on at most n elements in K. S times S, K is at most n. Okay? Then this is called the growth, and the exercise, if you don't know it, show that if S and T are two generating sets, then for some constant C1 and C and little c, we have that the growth with respect to S n is bounded by little c, the growth by t, and also the other direction. So every two growth functions are equivalent, and we can talk about the rate of growth. Okay? So in particular, sub-exponential growth means that, one definition is that if I take the nth root of this growth, and this goes to 1. Okay, so examples, abelian groups, nilpotent groups are also an example. And there are other stuff. There are stuff in the middle. Maybe I should say it. These groups have polynomial growth. And there are groups of exponential growth, and it was an open question for a lot of time, is there something in the middle? And I think Ergodic answered that the answer is yes. He gave an example, and I'll maybe put a link on the Dropbox to read more about it. Okay, so assume that this G has some exponential growth. Then if I let Fn be balls of radius n, so these sets, form a corner set. So again, I don't want to solve it here, but basically the main idea is to notice that if I take any epsilon bigger than 1, that's are bigger than 0, then for n large enough, we have this, the size of fn plus 1 over the size of fn, exactly. This is by 1 plus epsilon. Okay? And if gamma is inside the ball of radius m, then gamma fn is inside the ball of radius m. Okay? So, okay. Is the board here for me? No, it's not. So, okay. Now just deleting. Okay, so we have some examples of amenable groups. So here's a question. Are all say abelian groups amenable? So we have a positive answer if the group is discrete. Let's say what happens for v equals to r. Or other examples. So there are different ways of answering this question. I'm going to answer this with a theorem proved by Marco Campani. Saying the following. Okay. This is again this demand that we have on topological vector spaces. And again, I remind you that topology here is defined by the norms, the semi-norms, sorry. And that J be a collection of commuting elements, operators from V to V, which are defined. Okay, so now let K inside the V be a complex context set, and suppose that every transformation in J preserves this set K. Then there is an element of K which is fixed by all elements of J, simultaneously. Okay? So, is it clear that this theorem alone proves the amenability of abelian groups? Just plug it into the definition pretty much. So let's prove this theorem. step 1, which is probably the crucial step, to do it for J, which is a single transformation. So the idea here is as follows. Take some x and j and define xn to be that's the mean on the first k iterations, which lies in C, of course, because it's compact. It's convex, sorry. So it is compact, so xn converges in J to some point x. Now I claim that, well, x is a bad name, y. Okay. I claim that y is T invariant. So why is that? I remind you something that we said a few seconds ago. The topology here is defined by manners of seminorms. So let's take such seminorm. Compute. So maybe before writing this, let me just notice txn minus xn. This is just a telescopic sum. Okay? This is what I have. And I would like to say that because it is compact, it's bounded or something. So this remains boundedly away from the origins. Also, this remains boundedly away from the origins. We divide by n, everything goes fine. This is exactly why I introduced the seminorm. And now I can say this is actually 1 over n. None of these both lie in K, so there is some constant. No, big M, which belongs to sum, because K is compact. And this goes to 0. So the limiting guy y is exactly T invariant. Okay? This is probably the most important step in the proof. So, step 2 is, okay, so we have J, and we define CT to be, T invariant point in C. So this is non-empty, it's not. So we show if I take another point in J, x preserves CT, which is clear. If x is in CT, then s of x will be s of tx, because tx is x. But s and t commute by assumption, we have this. So something is t of something. S of x is t of x. Okay? So, step 3. So, but this is kind of clear. CT is compact and convex. And why is clear? Compact because it's a closed subset of something compact. Convex because T is defined. And so now we define if I have n operators in J, I can look at the intersection of these sets, and I claim this is non-empty. Why is that? So I know this for CT1. Now let me play this game for C, which is this set, and for the transformation, which is T2. So this is non-empty, and this is non-empty, etc., etc., etc. So now, last step, let us consider this. that it's non-empty. So how do we do that? Series compact. And if we intersect finite remaining sets here, I get something non-empty. Finite intersection property gives me that this is non-empty. So, should I remind what the intersection property is, or I don't think so, right? Okay. So we have showed that abelian groups are all amenable, and maybe I should make a comment for those who do know that one can show the following. It's not even that hard, I chose not to, that if I have some ordered collection of those amenable groups, and I look at the direct limit, the alpha, this is also amenable. One can also argue, after proving this, that the general abelian group or general group is just the direct limit of finitely generated subgroups of it. We already know that finitely generated abelian groups are amenable. Okay, so maybe just to illustrate the backward of what we did in the last part of yesterday, that we embedded F2 inside SL3. So something about the Merck-Tarski paradox.
Is Marx about discrete groups or not necessarily?
This is about general groups.
So what's the topology on the limit?
Just the general, it's the minimal topology such that all these maps are continuous. Okay? This is the topology. So, maybe a claim, just see a nice application of this. If G is amenable, and G, X, and X mix differently. If I have a left mean on G, I get a G invariant mean on X when Gx and X. Nice enough. Just by, if I have a function from X to R, then I just pick from X to X and look at these values, and now I average over G. So this gives me some invariant mean on X. Note that if I take F to be a characteristic function, I don't need continuity. I don't care about up to measure 0 and this stuff here. I'm sorry. So if I take F to be the characteristic function of some set, I get basically a measure which is left invariant, and it is defined on all subsets of X. In particular, I can't have paradoxical decomposition of X, which is what one sees in the Banach-Tarski paradox. So note that the groups SO2 is basically the circle group, and SO1, which is exercise. These are all abelian. So no paradox in dimensions 1 and 2. At least not for rotations. There are paradoxes for SL2 and 7. So I have some couple of minutes left, so what I haven't really got anything else prepared, so add questions. Okay, so maybe something off the top of my mind, so close was properly used. So, 1. If G is a group, local from a group, say discrete group, and H is some normal subgroup of it, and if I know that G mod H is amenable, and then that H is amenable. So one way to see this is if you take invariant mean of G mod H and H, you can somehow, with the formula we had in the first day, something like integral G mod H, integral H, integral G, to just make some invariant mean on G itself. This is one way to see this. And another property that I'm just trying to stop some time is that if H is a subgroup of G and G is amenable, then H is amenable. This is exercise. Well, 3. The 3 group is not amenable. So, one way to see this is that the action of the 3 group on itself is paradoxical. If we can just represent it graphically, and the colors. I'll use this. If I take this set and apply a left translation, I get this set. If I take this set up top and apply down translation, I get this set. So if I start with 3 again, then I decompose my group into 5 parts. So this, and this point, I can reconstruct more than 2 parts. 2 parts and some change. So I can't have that invariant mean because then 1 would be 2. So corollary, for example, is that if I have SL2 R is mathematical. Okay, and well, we'll see, I think, in a bit, if time permits, that we will discuss what is called property T. Some of you may know it, and say SL2R and SL2Z and all of this part, if I recall correctly, has the property T. And it is a general fact that groups cannot have both unless they are finite or compact. And this is not the case here. Okay, so this is just to steal 5 more minutes and talk about the future a bit. But